Okay, we'll move on to the next model. Now, continuing with supervised learning models, we will go to support vector machines. Now, talking of SVM, this is a classification algorithm. So far, whatever we've done, they've all been regression algorithms. The prediction algorithms is one more prediction algorithm that we are still to discuss, which is decision trees. But over here, we will be going to a classification algorithm. Now, there are quite a few classification algorithms that we have. We have support vector machines to start with, followed by you have k-means algorithm, then you have KNN algorithm. There are so many different algorithms that we have. Every algorithm will have a different strategy of classifying things. Now, depending on what is the data that you're working with, depending on what is the project that you're working with, accordingly, you've got to decide. Accordingly, you need to know. Accordingly, you need to know which is the algorithm that you will be working with. We will look at support vector machines and also another a priori algorithm today, which is a classification algorithm. So depending on the kind of results that you're looking at, you have to pick up a support. You have to pick up a proper classification algorithm. Okay. Now, what exactly is SVM all about? Now, guys, observe this. See, forget the theory part. Just understand this properly. See, suppose if I've been given some particular data and I want to classify it based on certain parameters, then how do we do that? Now, for a simple example, suppose I want to classify something. Let's understand this idea with a very simple example, and then we'll see how it needs to be implemented. Suppose we want to classify, say, a bat as a cricket bat or a baseball bat. So what's happening over here is that I have some particular data with me, and based on that, when you give me, this is some information pertaining to the bats. What I want is that once you've given me the data, I should be able to classify it as a baseball bat or say a cricket bat. That is what I need to do. So you see, this is something which you can use in image processing. You can use it in any place where you have the data available. You just want to click the image, or you just want to get some particular data and tell me whether it's a cricket bat or a baseball bat. Now, pertaining to these bats, there are so many different parameters that we can talk about. We can talk about the length, we can talk about the width, we can talk about the material used, we can talk about the cost, we can talk about the grip and whatever. But then we need to pick and choose which is the attribute which will help us in defining, or which will help us in distinguishing between a cricket bat and the baseball bat. The most obvious attribute is the width, because almost all cricket bats are going to be, say, slightly more wider as compared to the baseball bat. So that is the parameter that we need to try and understand. But let us try and understand, whenever you are passing the data, how will this algorithm go about creating that classification? How does, or what is the thought process behind this algorithm? Observe this. See, what we'll do is, suppose I have some data. Suppose I have some data pertaining to a cricket bat and some data pertaining to a baseball bat. I'll plot all that over here. Over here, just for simplicity, just I've put these images, and then based on those points, we will get this classification line. Now, once I get this classification line, whenever I'm plotting some data, if the data gets plotted on this side, we will say that this is a cricket bat. If it gets plotted this side, then we'll say that this is a baseball bat. So that is what is the whole idea. Now, needless to say, everything comes down to how exactly do I get this particular line, or how well can I get this particular line. If I can get this line to a good accuracy, then obviously my prediction model will give fantastic results. If there is some issue when it comes to plotting this line, if that is not the best possible, result, or that is not the best possible line, in that case, the results are not going to be as effective. So that is what we need to be looking at. Now, observe this. So over here, for simplicity, I'd put it like this, but let's just put it properly. Let's get something like this. Suppose for the cricket bats, the data that I have for cricket bats, I'll just plot it as, say, red colored circles and yellow colored circles for baseball bat. Now, what happens here is, see this. Suppose I've plotted these points. Let's keep this as an example. Suppose, say, the parameter that I'm looking at is the width. So obviously, when you talk of cricket bats, the width would always be higher. So you are getting all these red points on the higher side. That is what it is. And baseball bat, the widths are lower, so you will get widths on the lower side. See, that way, if you get a point anywhere over here, there is absolutely no doubt that this is a cricket bat. Or if I get a point over here, there is no doubt that this is a baseball bat. When does the issue come in? The issue comes in to these points. See, there might be a cricket bat. Maybe, see, when I say cricket bat, I haven't said the one which is used by professionals. Maybe for younger kids, when they play with cricket bats, they get those lighter bats where the width would be lesser. There might be an odd baseball bat where the width would be higher. So when you come to classification, if things are very obvious, then there is no issue. The issue is along these points. Now this is where I need to be careful with the way that I classify. See, if I just remove the colors, very easily this can get classified as a baseball bat. Very easily this can get classified as a cricket bat. So that is something that we need to understand. Guys, be it your regression algorithms, be it your classification algorithms, always understand this. They will go wrong. They might go wrong with an odd value. All we have to do is we have to try and minimize, or I have to try and minimize I have to try and minimize the error or the possibility of that error being generated, or you can say I have to try and get a model which is as accurate as possible. Now observe this. How is this going to work? So over here, what I want is I want a clear bifurcation. What did I tell you? I want a line like this. Moment I get this particular line, what happens? Moment I get this particular line, what happens over here is anything that is going to one side of this particular line, it becomes a cricket bat. On the other side, it becomes a baseball bat. The question is, how do I get this line? Now, if this is the data, I can get so many different lines. Option 1, the blue colored line. Option 2, green colored line. Option 3, red colored line. See, actually speaking, all three lines are creating a clear bifurcation between the points that represent the cricket bat and the points that represent the baseball bat. Now, the question is, how do I select this particular line? I'll try and compare and contrast all three lines, and I'm going to be giving you three technical words that you need to understand over here. There is going to be a word called margin, there is going to be a word called hyperplane, and there is going to be a word called support vectors. So these are the three terms that you need to understand. Moment you understand these terms, you will know how easy it is for understanding this algorithm. And then obviously we'll pick up a data set, and using that data set, I'll try and demonstrate how exactly the classification happens in this particular case. Now, please look at this. Let me try and analyze, say this line, say this blue colored line. See, suppose this is the known data that I have, say for cricket bats and say the baseball bats. Now, if I get this blue colored line, guys, observe this. I will calculate the margins. Now, over here, when I calculate the margin, say for the baseball side, over here, the closest point to this blue colored line is this one. So this is the margin that I have for say the baseball bats. But comparatively, the margin that I'm getting over here from say the cricket bat, now this red colored dot is the closest to this blue colored line. So this is what is the margin. Now over here, what I find is, suppose if I design this model like this, now over here, if I get a point which gets plotted over here, my model will say that this is a baseball bat. Whereas if you see, actually, isn't this closer to the cricket side? This should ideally be classified as a cricket bat, but my model will end up saying that this is a baseball bat because it is being plotted on this particular side of this line. Now, why has this happened? This has happened because the margins that I'm getting are not uniform. So this is not going to be a great bifurcation, or this is not going to be a great classification. Imagine if I get this particular line. Now over here, if you look at the margins, so compared to say the closest yellow colored point, I'm getting this margin and I'm getting very less margin over here. This is in fact even worse than your blue colored, this is worse than the blue colored line because the margins are so thin. The problem is, if I plot a point over here, this will be classified as a cricket bat. Whereas if you see, it is very close to these baseball bats. This could be a baseball bat, or maybe if I get a point over here, see, understand this will get classified as a baseball bat, whereas it is so close to being a cricket bat. So over here the margins are not great. See, the difference between the two lines is the slope. This blue colored line had a higher slope than this green colored line. But the point here is it's not about the slope, it's about the margins that I'm getting. Now, if the margins are not proper, if the margins are not taken care of properly, my model can keep giving you incorrect results at all times. But in comparison, look at this particular line. If I can get a line like this, where the margins are pretty even on both the sides, or you can say I'm getting the maximum possible margin over here. If I get this, I'll call this as the best fit line. Now over here, the nearest point, say from the red side is this, and from the yellow side is this. Now over here, if I get a point even close to this will be classified more of, say, a baseball bat. Or if I get a point closer to this, it will be classified more of a cricket bat. See guys, I'm not saying that this model cannot go wrong. There cannot be a model that cannot go wrong. What if I get a point like this? Possible. But understand this, the probability of this model going wrong is much lower, is much lesser. So this is how we need to get the bifurcation. Now the key here is, when you have the training data and when you are carrying out the classification, the question is, how do I get this particular line? Now, moment I get this line, my job is very easy. The key is, how do I get this particular line? And that is exactly what support vector machine algorithm is going to do for me. Whenever you give me any data, what it will do is it will bifurcate this particular data by using some particular approach. It will give me the best fit line, and based on the best fit line, I will then go out and carry out what is called as the classification of the data. This is what we intend to do. Now observe this. How is this going to work? When I apply SVM, it will come down to three technical terms. What are these three terms? See, this margin I've already spoken about. I'm always looking for maximum margin. When we create these margins, we will calculate these margins from the points which are the closest to this margin, right? Or which are the closest to this plane that I'm trying to design. Now, from the baseball side, this is the point. From the cricket side, this is the point. These points, they are what are called as support vectors. So basically, support vectors will be the reference using which I will decide what is the line which will bifurcate, bifurcate this data. This best fit line that I get eventually is what is called as the hyperplane. So the whole idea behind support vector machines is that you need to design a hyperplane based on which you can classify the data. Now, for getting the hyperplane, I need to first get the support vectors, and I need to identify the support vectors in such a manner that I'll get the maximum possible margin. Now, once I get that particular margin, I will get the system, and then I'll try and classify whatever I want to based on that classification. That is the idea. This is what I intend to do. How this is to be done, we are still to discuss that, but this is what we intend to do. Any doubts with the concept? What are we trying to do? Is that understood? Any doubts with that? Because then I'll get into the technical part of it. Okay, so now how exactly are we going to get that? Now, first of all, why is it that we are using the term hyperplane and not the best fit line? Or why we are saying that it is not a line? Now guys, just observe this. This can confuse you a bit. I'll explain this whole concept with a proper program, but before that, why did I use the word hyperplane and not a line? Please understand this carefully. See this. See, suppose if I talk of the bats. So the parameter here is whatever, and say here is the width, right? Then what I can do is, whatever the points that you've given me, say for cricket bats, and whatever the points that you've given me, say for baseball bats, I get this line and my job is done. See, this is because there was only one parameter that was required to be considered before we could decide whether it is a cricket bat or whether it is a baseball bat. So then I could have easily used the term align. But guys, observe this. It does not always happen like this. Suppose there are multiple parameters to be considered. Say maybe width is one, and I should also look at, say, the length of the bats. So now this becomes a 3D thing. Now if I'm plotting a point like this, observe what happens. See, when you had one single line and when you had plotted these points, for evaluation or for us to be able to identify what is happening, we could have just dropped these points on this line. So I'll drop this point here, I'll drop this point here, I'll drop this point here, like this. And these points would be dropped over here. And now if I draw this line as a straight line, I'm drawing this line. It has points here. It has points here. So there is a clear bifurcation. Anything that gets plotted over here is a cricket bat, and anything that gets plotted over here is a baseball bat. This is what would have happened. Now, how did I get this? There was just one parameter. I just drew a line and we were just getting it like this. Now, if there was only one parameter width, I could have easily decided this. But now this is a 3D plane. Over here, I cannot just drop these lines or these points on say W or L or say X. I cannot. So what we'll be required to do is over here, we will be required to draw a plane like this, which will represent all the coordinates. And these points will then be dropped onto this plane. And then based on what is happening on this plane, I will have to make the necessary predictions. That is why we use the term hyperplane. It could be 2 parameters, it could be 3 parameters, it could be n number of parameters. That is why the term hyperplane. Your idea of support vectors will also change. Your idea of classification will also change. That is why the term hyperplane. So this whole concept of support vector machine works on this particular term or these 3 terms. What are the 3 terms? Support vectors, margins, and hyperplanes. That is what is going to happen. Now what we'll be doing is we'll take up a proper data set. We will analyze that particular data set. We will design a support vector machine and we will try and figure out or we'll try and find out whether we can classify something using a support vector machine over here. So I'm going to go to the data set. I'm going to go to the case study, and based on that, we'll try and understand this concept. But at least this is clear. Whatever we've discussed till this point, what exactly we are planning to do, is that understood? Any doubts with this? Because if you understand the funda, then it's very easy. I've been telling you this. I'm not bothered about the codes at all because they're all standard codes. You're not required to make wholesale changes to those codes to implement your own systems. Once I finish this, immediately you will be able to design a support vector machine for any data set that you have. Okay. Let's try and understand this with an example. Mayura, summarize what is the point? Tell me. What is it that you've not understood? I'll go to that. Which point? The 3D part. See, what we were trying to understand over here is that support vector, when we are drawing, we have used the word plane. We never said that it's a line or like in linear regression, we said that it's a best fit line. Over here, we are saying hyperplane, which is the best fit plane. This is because whenever we are plotting a point or whenever we are trying to categorize something or classify something, it's not always necessary that using just one parameter I will be able to classify. Suppose for me to be able to identify a cricket bat or a baseball bat, I need to look at both the parameters, say the width and length. In that case, there are multiple parameters that we are required to consider. In that case, whenever I'm plotting the points, these points will get plotted in a 3D environment. Now, whenever the data is in a 3D environment, you cannot just plot it to one single line the way I could have done it with say a 2D environment. If it's 2D environment, you can easily plot these points on the straight line and get the job done. But when you are in a 3D environment, you will have to create a plane which represents the values on all three axes. And then once you get this plane, you will plot these points on this plane. So anything that needs to be analyzed has to be done on this plane. That is why we've used the word hyperplane. Now, all this the system will do on its own. If you give it one parameter, it will create a hyperplane, which would be a single line. If you give it multiple parameters for deciding whatever it is, then the system will create a hyperplane. You will have a function which will do everything for you. But this is what is going to happen in the background. It will first plot all the points that you have in the data. It will project it on the hyperplane. Then once you give the testing data, it will go to the hyperplane, plot that point on that hyperplane, and depending on what part of hyperplane it is plotted on, it will be classified as whatever you are trying to get. So that is what is going to happen in this particular algorithm. Now, so back to this slide. So three terms you need to understand. Support vectors. Support vectors, what are support vectors? Support vectors are those points which are the closest to the hyperplane that you are going to design. So you will be calculating your margins from the support vector. So that is what it is. Support vector machines. Margins, support vectors, and hyperplanes. Okay. Now what I'm doing is I'm going to a data set, and using this data set, I'll first create a support vector machine, and then based on the support vector machine that we design, we will try and make some predictions. Now, what is this data set all about? Now, we have a data set called recipes for muffins and cupcakes. See, basically, the data set is like this. I have 21 recipes available to me. Some of these recipes are for muffins, and some of these recipes are for cupcakes. Now, what I need to do is I need to design an SVM using which I can just look at that particular recipe, and I should be able to classify whether it is related to muffins, whether that recipe is for muffins or whether the recipe is for cupcakes. So that is what is the aim. So what we'll do is we will have a look at that particular data set. We'll try and understand what do we have in that data set, and then we'll design that model, which when required will tell you, when you give it the data, it will tell you whether that data is representing muffins or whether the data is representing cupcakes, or the recipe for muffins and the recipe for cupcakes. Now, what exactly is this? Observe this. See, whenever you talk of a recipe will talk about certain ingredients that are required to be used for cooking anything. Now, if I look at my data set, now this is the data set that I have. Now, what we've done is the 21 recipes, sorry, we have 20 recipes. Of the 20 recipes that we have looked at the ingredients. So what we found is that all these recipes, they talk about the quantity of flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we found is that whenever we had recipes for muffin, say the first recipe which was of muffin, it spoke about these quantities of these products. Then I had another recipe for muffin. See, it's not necessary that the two recipes for the same thing will always be exactly the same. So this recipe of muffin had these ingredients. So this is how we had about, say, 10 recipes for muffin, and this is the breakup of the ingredients that they were talking about. I similarly had 10 order recipes for say cupcakes. So over here, what we find is that when I break up the ingredients, these are the list of ingredients that we have. Now, this is the data that I have for designing this model. Now, using this data, I'm going to design this model. And what should happen is later on, when you give me the quantity of something, I should be able to tell you whether this is muffin, or this recipe is for muffin, or is this recipe for a cake. That is what this is all about. Now, guys, just observe this. Now over here, what you need to do is you need to look at the ingredients, and you need to decide that, okay, these are the two ingredients that I should be looking at, and using that, I should be able to classify whether this is a muffin or whether this is a cupcake. So that is what we need to do. See, like if I had to go for say cricket bat and baseball bat, there can be n number of parameters. Now one could be the type of the wood used. Now, I don't know, maybe it is possible that we can make a cricket bat with the same wood that is used for say baseball bat, or vice versa, So what is the type of the wood used? It might not help us understand anything. But what I clearly know is that the width of the bat is a clear indicator, of whether it's a cricket bat or a baseball bat, because cricket bats are generally, or more often than not, wider than that of the baseball bat. Or maybe even the weight. I think cricket bats are heavier than that of the baseball bats. But again, that can be disputed. There might be a baseball bat, or the average baseball bat might be as heavy as a cricket bat. So we need to think about the parameters which can help you, and accordingly you need to decide what it is all about, right? Now observe this. How exactly are we going to do this? Now over here, I've started by importing. Okay, let me create again. Okay, now what I'll do is, as always, I'll just zoom this. Okay, as always, I've started by importing all these libraries. I have pandas, I have numpy, I have sklearn, and then I have matplotlib as well for plotting the graphs. Now the first thing that I need to do is I need to read the file, and I need to open that particular data set that I have. Now pd.read CSV. Now this is where I'm reading a CSV file. So the data that is stored on my system is not an Excel file, it is a CSV file, comma separated values. So I'm opening this particular file, and as always, I'm just displaying the head just to check whether the file has opened properly. Now when I run this, yes, it has opened properly. Now this file currently has, say, 20 entries. Now it could have been 20,000 entries. It doesn't make a difference. I don't have to change my code at all with the change in the numbers. It doesn't make any difference to us, right? So over here, we've opened this particular file. We have opened this particular file, right? So this is what we've done. Okay, now going further, what I'll do is I'll first just plot. Suppose I have decided that the two parameters that I'm going to consider for classifying the recipe as say a muffin or cupcake is the quantity of the flour used and the quantity of the sugar used. So these are the two parameters. So what I'm doing is I'm going to get a line plot for these. I've decided two ingredients, so I'm going to get the line plot. So using Seaborn, I'm going to get this line. I think I forgot to import Seaborn. Okay, I'll import that. So Seaborn. So flour and sugar is what I'm looking at. From where? From this particular data frame called recipe, right? And then it's up to you how exactly is you want to plot it. So fit and all. See, palette is you can choose the colors randomly, and scatter. This is 70 is the size of the points that you need to plot in the scatter plot. I'd forgotten this. I need to import Seaborn as well because I'm using SNS out here. Okay. Now when I run this, basically what it is doing is it is plotting these two things. What? See over here. See over here, the blue colored ones are for the cupcake, and the red color ones are for muffins. Now, guys, just observe this. Based on the quantity of flour and sugar, on the x-axis we've taken flour, on the y-axis I've taken sugar, and then that particular and then based on the quantities that are available in the data set, what we've done is the quantities that are available in the data set is accordingly we've plotted these points. Now coming back to these points, understand this. See this. This is the graph that I've got. Actually on the spider screen there the pen doesn't work there. Now over here I want to create a clear bifurcation between a muffin and a cupcake. Suppose, say, if I can get something like this, I don't know, right? If I can get something like this, then later on anything that gets plotted on this side can be classified as a muffin, and anything that gets plotted over here based on the data that you give me can get classified as a cupcake. But guys, understand this. Now when I'm trying to get this hyperplane, what I need to understand is I need to first identify identify the support vectors. Now in this case, if the line has to go somewhere between this over here, then this is going to be my first support vector, this is going to be my second support vector. So based on this we will be plotting these lines, right? And accordingly we will work. Now looking at this graph, it is pretty obvious that whenever you are talking of cupcake, the amount of sugar is always higher in cupcake as compared to muffins, right? Whereas the quantity of flour is lesser in cupcakes and higher in muffins. So that is what we can figure out from this particular graph. So I've got this particular point, these points, and based on these points, what I'm going to do now is I'm going to create a hyperplane. If you change the value of S, the points will get bigger, the points will get thicker. So we've got a line plot over here. See, that is why I keep saying that you study data visualization in Python. These are all predefined functions. We're just passing the data and then getting the job done. Okay, so now we've got the data, we've got everything over here. Now what we need to do is we will now need to pass the data and then design the model. Now we are over here trying to specify the parameters that are required to be considered for designing the model. See, again, I repeat, we haven't started designing SVM as yet. What we are doing is data collection and data analysis, and if need be, I'll do data wrangling. But looking at the data set that I've got, I don't think there is too much of, there's hardly any missing data. There aren't too many values. I don't see there is any issue. Or maybe if I want to do data wrangling, the two columns that which you can drop are vanilla and salt, because if you see salt, if there is no requirement of salt, if none of the recipes are talking about salt, why do you even have this column called salt? So you can drop this one, you can drop vanilla as well, because it's not going to help you in any given way. So maybe just dropping these two columns would be sufficient here for data wrangling. But now just observe this. How are we going to work? Now what I'm going to do is I'm required to work with the two columns called flour and sugar, right? The entries from these two columns. But now when I'm designing SVM, I'm required to pass the data as a matrix. So that is what we've done. See, if you want, you can actually see this. What I can do is print. Now I'll just run till this time. I'll remove this also, head. Sorry. Now when I run this, see this. See, what has it done? It has basically converted the quantities of flour and sugar into a matrix. So for the first recipe that we had, the quantity of flour was 55, sugar was 3. For second one, it is 47 and 12. Third one, the quantity of flour was 47 and sugar was 18. So basically, what is the statement doing? This statement is taking all the attributes that you are required to work with, or all the data that you are required to work with, and convert it to a matrix, right? So it's a multi-dimensional array that is created. So as matrix is a function available in Python which converts this for us. Now what I'm doing is type label. Now np is numpy. In this particular recipe, wherever I have muffin, it will put it at 0, and wherever it is say cupcakes, this becomes 1. So over here, what these type labels will do is, in the data frame that we are working with, 0 will be used to identify a muffin and 1 will be used to identify anything other than muffin. In our case, that anything that we are talking about is nothing but a cupcake. Now if you want to see that, you can print these as well, but no, you're not required to print these when you're designing the models. So if you see, this is what is happening. This is what is happening because of this statement type label. What are type labels? So in our data set, what has happened is we had 10 recipes for muffins first. That is why we've got these zeros, and all other recipes were for cupcakes. So that is where we've got 1. It's not necessary that you'll get all zeros and all ones together, because in my data set, all the recipes for muffin were together. That is why it was all zeros. All the recipes of cupcakes were together. That is why we've got all ones. See, if we had a mix, few muffins, few cupcakes, few muffins, few cupcakes, then we would have got 0 1 0 1, that particular combination. So in these two lines, line number 19 and line number 21, what I've done is, whatever is the data that I'm planning to work with, I've converted that into matrix, because the SVM function or the SVM module that I'm going to be working with, it needs the data in the form of a matrix. And second, in my recipe or in my data frame, I needed type labels. So for the type muffin, it is replaced with 0, and for the type cupcakes, it is replaced with 1. Now what we'll do is we'll extract out the features that we are required to work with, and then what we'll do is we will convert them into a list. See, again, basically all I'm getting over here is a list of all the features. Always put a print statement and immediately you can see what's happening because of that particular statement. See, if you see, I've got a list. What is this list? This list is a collection of all the features that are available for the classification. In simpler terms, you can say whatever are the columns which are available in that particular data set, all that is now all that is now created over here. So we've converted them into a list. So that is what we've done over here. So you've got recipe features here. So this is how it is going to work. Right. Okay. Now that everything is ready, now I'll go and design a support vector machine for you. Again, the same thing. We are going to create an object and we are going to call the fit function, and then the rest of the code will be done. Everything would be done by the system. You will never be required to touch that particular code. Yahan se what I'll do is I'll make sure that the code is always such that it is generic. So honestly speaking, whenever you are designing a model using an SVM, you will be required to change whatever you see till say about line number 24. From over here, things are going to be the same, which we'll use as it is. Now, over here, what I've done is from the module SVM, I'm calling this function SVC. This is going to create your support vector machine, and kernel is equal to linear. See, there are different types of kernels, so there are different types of planes that you have. The one which we are using over here is linear. So depending on the type of the data that you're working with, you need to decide the kernel. Majority of the time, the linear kernel will work for you. Once I get the object of this particular class of support vector machine, what I'll now do is, as always, a fit function. So entire model design is going to be done by this. What have we passed to this particular model, this fit function? We've passed whatever other ingredients that we are interested in working with. So basically we are passing the quantities of flour and sugar. Basically we are passing the data of all the points that we have in the in that graph, and then the type label. So what it will do is it will then be able to correlate. The first point is 0, the second point is 0, so it knows the first point is muffin, second point is muffin. So third point, if it was 1, it will know that it is cupcake, and so on. This is where my model will get created. Then comes the entire set of calculation, where the system will calculate all the points and decide the hyperplane, the points which we are never required, or the part of the code which we are never required to change. If you ask me, have I written this? No. Whenever you have an SVM, this part of the code for the model design is always the same. What it will do is it will just keep plotting the point. Line space is a function in Python which will generate points for you. So over here we are generating 60 points between 0 and 30, and then accordingly we are plotting the new points x6 and y. So over here, this is that part of the code which you are not required to change at all. See, what happens here is, what I can tell you in simpler terms is, without complicating things too much, see, when we get this graph, suppose these are the points that we have for cricket bat, and these are the points that we have for, say, baseball bat. Obviously the coordinates are x and y. Now when I design this hyperplane, I'll basically drop these points here. This is the classification that we'll have for say cricket bats, and I'll drop these points here. This point will be dropped here, this point will be dropped here, right? And then when I draw this line as a straight line, these are my first 3 points, these are my next 3 points, and then there is this bifurcation. This is cricket bat, and then this is baseball bat. We've seen this earlier as well. But guys, understand this: if this point is, say, x and y, when I shift it over here, the x coordinate has changed and y coordinate has changed. So that is given as xx and yy in that program. So this is, you can say, the projection of that particular point on the plane. So the projections are created for that particular point, and based on that, we will now create the classification. All this will happen automatically. Moment I've said the linear plane, the system will automatically do this for you. So whenever you say x6 and yy, basically we are talking of the projected points or the projection of the actual points, and x and y will x and y will actually give you the original points. So this is where the system will actually generate the hyperplane. This part of the code we are not required to touch at all. System will generate the model on its own. Now what I'll do is I'll plot. See this. Now again, actually speaking, my model design is over. Now whatever graphs I'm plotting, this is only for you to see that whatever we were discussing, what exactly is happening in the background. So this code now from 46 till about 56, whatever I'm actually plotting or whatever I'm drawing, this is actually not needed when you're designing the model. This is for us to see that how this model is working, right? So this model design, the part of it has already been taken care of over here. But look at this. Now what I'm doing is I'm getting a line plot over here, right, with flour and sugar. Data is recipes and everything. But if you see, when I'm plotting, now I'm not plotting x and y, I'm plotting x6 and yy. Basically what I'm doing is the system has tried to identify a hyperplane, and then it has projected all the points on that particular plane. What if I plot those points? What do I get to see? See, observe this. So you see this blue colored lines that are happening. You see this, all these blue points and all these red points are on the same line. Now how did that happen? See, earlier this was the graph. I just spoke about a straight line that the system will take and project all these points. It has projected all these points, and that is why you can see, this blue colored lines and sorry, this blue colored points and then this red colored points. Now based on which, based on these points, what we are going to do is we are going to design a hyperplane which will pass through these points. So this black colored line is actually the hyperplane which has been decided over here. So if you see this code that we have designed over here, we've created the model, we've projected the points on that hyperplane, and depending on the values of x and y, we have plotted this hyperplane. Now based on this hyperplane, the classification is happening. Now if you want to see the support vectors also, we can do that as well. So I'm just showing you how it has calculated the support vectors. Again, when you design these models, these codes are not required. These are some extra codes which are just meant for displaying things. For learning purpose, we are doing this. Now again, we've got this line plot. What we will do is we will find the closest point on both the sides to this hyperplane, and then we will draw two lines passing through it. So that is what you will find over here. Now see this. Now if you see these two lines are clearly passing from the two nearest points that you have on this particular line. So those 2 points from which these dotted lines are passing, they are nothing but your support vectors. So they are your support vectors. So if you see, when I've drawn this support, I've drawn this particular, when I've drawn this, see, initially these two lines are just plotting the blue and the red points that you've seen earlier. Then what we've done is we've got the points required for the support vectors, and then we've plotted the support vector. So again, even over here, model is the object of class support vectors. 0 is the first support vector. 0 is for muffins. So this is the muffin support vector, and this is the cupcake support vectors that we get over here, and that is what has been plotted. But again, when you're designing the model, you're not required to actually plot all these things. So this will all happen in background, and you will get your results. Now what I'll do now is I now have a model. I'll now design a function. That function will accept the data from me, and then whatever is the data that I get, I'll pass it onto this model, and this model will tell me that based on that data, the recipe that I'm talking about, is it the recipe for muffin or is it the recipe for a cupcake? So that is what the model is going to be doing. So far what we've done is we've done the classification thing. So classification SVM is precisely about these 10 lines of code from line number 27 to 44. Again, I've made sure I've not gone for anything specific to this particular question in these lines. And you never do that with models. That is the standard practice when you're working with ML. And whatever changes are required to be made, the changes are required to be made over here. What is the data set that you're working with, you want to work with, or what is the attribute that you want to work with, and accordingly, the system will work. Now observe this. Now guys, see this. What I'm going to do is I'm going to write this function, which is muffin or cupcake. It will accept two values from you, the flour and sugar. Now, once I get this, I'll pass this particular data to this function called predict. Again, fit function tha. Now you have this predict function. Predict function will always get you the answer. It will carry out the predictions required. And if this value comes out to be 0, we've seen that we are representing muffin as 0. If this value comes out as 0, that means it matches with muffin on most cases. I'll say that it is a muffin recipe, else I'll say it is a cupcake recipe. We just have to pass this to this predict function, and the predict function will work on based on the data that we've used for designing this model. Now observe this. I'm going to ask the user the quantity of flour. I'll accept it. I'll ask the user the quantity of sugar. I'll accept it. I'll pass that data to this function, and the function is then going to predict whatever is required. Now if I run this entire code, enter the quantity of flour. Suppose if I say 25, enter the quantity of sugar. Suppose I say 7. It says you are looking at a cupcake recipe. Actually speaking, I'm not required to draw those graphs and stuff. This is the only thing that I'm required to be displaying in the output whenever I'm designing a model. This is what I'm supposed to be doing. Rest everything is actually extra, just to show you that these are the points. This is how a hyperplane is created. This is how the points are being projected. This is how these are the values of the support vectors that we are talking about. But honestly speaking, all I need is this one. You should ask me the quantity of flour, you should ask me the quantity of sugar, and then you can predict whether it's a cupcake or whether it's a muffin. Now over here I've gone with two parameters, say which is say sugar and what flour. If you want, you can change it to whatever you feel like. Say suppose if you say butter and sugar, accordingly you make the changes. Wherever you have flour, you just change it to butter and it will work for you. So for the different set of data, you'll get different points. You'll get different you'll get a different graph. You'll get a different support vector. You'll get a different hyperplane, and then obviously the results would be generated something like this. So this is how you'll design a simple support vector machine, pass the data and make the prediction. So this is a prediction model. Now anything, now if you say I have some information about cars, I want to identify that what type of a car is this, I can always apply SVM. If you give me certain features which will help me differentiate the cars, I'll just feed that particular data and I'll be able to classify it for you, whether it's a muffin or a, like I defined over here, muffin or cupcake. I can actually define whatever is the type of car. Now suppose if you want me to test, if you tell me okay, I have these 100 values and I want to check all 100 recipes whether they are muffin or a cupcake. So what I'll do is I'll just write a loop, and in that loop I'll keep passing the data to this function, and this function will start giving back the result. So that is how it is going to work. Is this fine? So that is how you'll design a support vector machine. Any queries with this, please? Say if there are more than two types, it doesn't make a difference. All you have to do is when you are passing the data over here, see, uh, see, when you're passing the data over here, you will be required to give three parameters. If you want to work with three parameters, you'll have to give three parameters or four parameters. This as matrix function. Now, because there were two values, it created a matrix of it created a two-dimensional array. If at all it was three parameters, it will get three-dimensional arrays, four-dimensional arrays. You can have n-dimensional arrays. The way in all programming languages we have n-dimensional arrays, over here NumPy will give me an option of creating n-dimensional arrays. So system will take care of that on its own, and then when it is creating the plane, it will create the hyperplane accordingly. So it doesn't make a difference. You can use any number of parameters that you feel like. This is where you will be required to make the change. Yes, support vector machine. Keep things simple. They are pretty